let's see how we are going to prove that n factorial is greater than 2 to the n for n is greater than or equal to 4. So this means n starts at 4, and then the next number, which is 5, and then 6, and so on, so on, so on. So here we have a statement involving positive whole numbers, so we can try to use the mathematical induction. Let's go ahead and put down the PF first, and we are going to check the base case. In our situation here is when n is equal to 4. And I just have to plug in 4 into both sides and see if the inequality works or not. So we have 4 factorial versus 2 to the 4th. Well, is this greater than that? That's why I don't know yet, so I'll put on the question mark. But this right here means 4 times 3 times 2 times 1, which is 24. And this means 2 times 2 times 2 times 2, which gives us 16. So of course, 24 is greater than 16, therefore the base case checks. So we are done. Now, the next step is that we are going to do the inductive hypothesis, and let me write that down for you guys. Here, inductive hypothesis. What we are going to do is assume our claim is true for some variable, and let's use k for that. And let's write it down specifically. Assume this is true for k, so I can plug in k into here and also here. So we have k factorial is greater than 2 to the k. And we will also have to mention this right here. I will say for some positive whole number k that is greater than or equal to 4. And in fact, you don't have to mention the equal to 4, because when k is equal to 4, that was the base case and we knew it was true. But if you keep it like this, that's fine too. Now, once we have the inductive hypothesis, our goal is to check for k plus 1. This means, can I plug in k plus 1 into the n right here, and we have the k plus 1 factorial. Can we show that this is greater than, again, put k plus 1 into this n, so we have 2 to the k plus 1. This is our goal. So let's just go ahead and check. I am going to start off with k plus 1 factorial. Firstly, do the algebra. We can break down the k factorial as k plus 1 times the next one, which is just k, and then keep going, k minus 1 and k minus 2 and so on, right? But it's really just k factorial. So this is equal to that. Done. Now, how do we continue? Here is the part that we will have to use the inequalities. What inequalities do we have? The inductive hypothesis. Do we see the k factorial? Yes. This part has the k factorial, and by our inductive hypothesis, k factorial is greater than 2 to the k. So let's do this. K factorial is greater than 2 to the k, and let's write that down. K factorial is greater than 2 to the k. Yeah, just like this. And then let's write this down. Parentheses, k plus 1. So we are making a progress. Now, what can we do next though? Well, again, let's see what this is actually. This is 2 to the k plus 1, and that's just the same as 2 to the k times 2 to the first, and that's really the same as just 2 times 2 to the k. So we have 2 to the k right here already. In the front right here, I want to have 2, but this is k plus 1. So can we get that though? Again, go back there and see if we have any inequalities that we can use. K is greater than or equal to 4. So I'm going to replace this k with 4 and use the inequality greater than or equal to. Just like that. And then the rest right here, just keep it. Now, what else can we use though? Well, this is 4 plus 1, which is 5. 5 is definitely greater than 2. 5 is greater than 2. And the reason that I put on a 2, not 3, not 4.5, why not? It's because I really want you to end up with this expression. And this is clearly true. You can write it down because 5 is greater than 2. And right here, you can also mention because of the inductive hypothesis. And right here, you can also mention that because k is greater than or equal to 4. So that's pretty much it. And then times 2 to the k. Now, ladies and gentlemen, this right here is equal to 2 to the k plus 1. That is exactly the goal. That is exactly the proof. Put a box, shade it in, and we are done.